All right. Welcome, students. Welcome. Today we're going to be looking at the 2013 Cape Mathematics paper. And before we begin, I just want to mention that you shouldn't look at previous past papers from 2004 to 2012 because they were using a different syllabus at that time, and the syllabus changed in 2013. And so there will be no solution for 2004 to 2012 because the syllabus changed. All right, so stuff like complex numbers and all of those stuff, they moved it from module 3 to module 1, etc. So focus on 2013 to 2020. All right, let's get it. So question 1 says, calculate the gradient of the curve ln x squared y. So let's do that. That's question 1. So you have ln x squared y minus sine y and this is equal to 3x minus 2y. And they want the gradient. So let's do this question. So first thing is, I know that with log functions, I can separate them. So I can separate this as ln x squared minus ln x squared plus ln y. I might ask, sir, why would you want to separate them? I want to separate them so I don't have to use I don't have to use composite rule to differentiate this. I can just differentiate it normally. Then I differentiate sine, well, I don't start differentiate yet, so I just write minus sine y. That's equal to 3x minus 2y. So all I did was use laws of logarithms to rewrite ln x squared y as ln x squared plus ln y. Now when I have this now, I can differentiate now. So now I'm going to differentiate both sides. So I'm going to differentiate both sides with respect to x. All right, d by dx. So when I differentiate both sides with respect to x, to differentiate ln x squared, I carry down the power. So I get 2 ln x. I subtract 1 from the power and multiply it by the differential of inside. Carry down the power, subtract 1 from the power. Or if you don't want to look at it that way, think of it as 2 ln x. To differentiate 2 ln x, when you differentiate ln x, you get 1 over x. All right? So let's do it that way. Instead of writing it as ln x squared, think of it as 2 ln x. And to differentiate 2 ln x, you just differentiate ln x. When you differentiate ln x, you get 1 over x. So it becomes 2 over x plus, when you differentiate ln y, you get 1 over y, but then you multiply it by dy by dx. In that case, I'm going to write y prime minus, when you differentiate sine y, you get cosine y. But then you multiply it by what? By dy by dx, which is y prime. And that's equal to, when you differentiate 3x, you get 3 minus, when you differentiate 2y, you get 2 y prime. So what you're going to do now is group everything with dy by dx on one side. So let's go ahead and do that. All right, let's bring everything with y prime on this side. So we're going to have 1 over y times y prime. Then we're going to have minus cosine y times y prime. Then we're going to have plus 2y prime. And that's going to be equal to, bring everything else to the other side. So we have, that looks like 3 minus 2 over x. Okay, nice. So all we're gonna do now is factor out y prime. So we're gonna factor out y prime, which is dy by dx. Factoring out y prime, we get 1 over y minus the cosine of y plus 2. That is equal to 3 minus 2 over x. Okay, nice. So all we have to do now is divide both sides by 1 over y minus cos y plus 2. So when we divide both sides by that, we're going to get that y prime, also known as dy by dx, is equal to 3 minus 2 over x, all being divided by 1 over y minus cos y plus 2. Nice. But we have to remember what the question had asked us. The question had asked us for dy by dx, I believe, when x is 1 and y is 0. So we need to find dy by dx at the point 1, 0. So we're going to substitute x as 1 and y as 0. Substituting x as 1, we're going to get that dy by dx, or y prime, is equal to, plugging in 1 right here, we get 3 minus 2, which is 1 over, plugging in y as 0, 1 over 0. 1 over 0 is a big number. That's infinity. All right, so we're going to write 1 over 0. And the cosine of 0 and the cos of 0. What is the cos of 0? I believe the cos of 0 is 1. So the cos of 0 is 1 plus 2. Now again, 1 over 0 is infinity, and 1 over infinity is 0. And so what we're going to get then is dy by dx, or y prime, is equal to 0. All right, why? Because it's 1, it's approximately equal to 1 over infinity, and 1 over infinity is equal to 0. And so the gradient at 1, 0 is 0. So you can give them a concluding statement. That is, the gradient is 0 at the point 1, 0. Gradient is 0. So if the gradient is 0, we know at 1, 0 it's a stationary point. Nice. Now let's look at the second part of the question. Question 1b. Question 1b, this is a partial derivative question. It gives us a function f of x, y, z, and it tells us that f is equal to 3y z squared minus e to the 4x, and e to the 4x is being multiplied by the cosine of 4z minus 4. And they tell us that this function is also equal to 0, which I think that part is irrelevant, that it's equal to 0. But nonetheless, let's see what they're asking. They said, given that dou z by dou y is equal to minus dou f by dou y over dou f by dou z, determine dou z by dou y in terms of x, y, and z. So no problem with doing this question. So they give us what is dou z. It is dou f by dou y over dou f by dou z. So first we need to find is dou f by dou y. Let's find that first. So we need to find dou f by dou y. To find dou f by dou y, we think of everything else as a constant. All right. So Z square here is like a constant, and so differentiating this, what we're going to get is we're differentiating with respect to y. So it's going to become 3z squared, because z squared is a constant now. No, oh, something was missing out of the question. Missed out something out of the question. I was like, why it looks so short? It was e to the 4x times cosine z minus 3y squared minus 4. Now the question is finished. So differentiate this part. Now let's differentiate this now. Now differentiating this with respect to y is 0, because that's just a constant, so you get minus 0. Then you have 3y squared, you carry down the power, and you subtract 1 from the power. So dou f by dou y is 3z squared minus 6. Now next thing we need to find is, we need to find dou f by dou z. We need to find dou f by dou z. So to find dou f by dou z, we're going to differentiate with respect to z. All right. So dou f by dou z, differentiating with respect to z, we carry down the power to get, so this becomes 6y and 6yz. We carry down the power and subtract 1 from the power. Now e to the 4x is a constant, so it's going to be minus, when you differentiate cosine, you get minus sine, and you multiply it by the derivative of cos 4z. When you differentiate cos 4z, you will get minus 4 sine 4z. So that's going to become minus and minus, make it be plus. So it's going to be plus 4 e to the 4x times the sine of 4z. That's it. That's dou f by dou z. Now you cannot differentiate this with respect to z, or you get 0. So now we can go ahead and write down what is dou f by, what was that? Dou f by, well, dou z by dou y, that is. We can now find dou z by dou y. Dou z by dou y is equal to minus dou f by dou y. Minus dou f by dou y is going to be 6y minus 3z squared divided by dou f by dou z. Dou f by dou z, it is 6yz plus 4e to the 4x times the sine of 4z. That's dou z by dou y. Nice and easy, soft. Right, so this is that question. Soft. With a capital T. Let's look at the next part of the question. The next part of the question says, using the Marvelous Theorem, we want to prove that the cosine of 5 theta is equal to 16 cos to the 5 theta minus 20 cos cubed theta plus 5 cos theta. So we want to use the Marvelous Theorem. So this was part B, and let's start part C down here. So using the Marvelous Theorem, first we need to remember what the Marvelous Theorem is. The Marvelous Theorem started by saying that the cosine of theta plus I sine theta raised to the nth power. So cos theta plus I sine theta raised to the nth power by the Marvelous Theorem, this is equal to cos n theta plus I sine n theta. All right, this is the Marvelous Theorem. And we're going to use the Marvelous Theorem to prove this question. Cos n theta plus I sine n theta. Now, if you're to let n equal to, let n be equal to 5. If you let n be equal to 5, what are you going to get? If you call n equal to 5, all right, so let me write it here. Let n be equal to 5. If we put n equal to 5, what we're going to get is the cosine of theta plus I sine theta. All of this is raised to the 5th power. So cos theta plus I sine theta raised to the 5th power, that is going to be equal to cosine 5 theta plus I sine 5 theta. Nice and easy. That's what we're going to have, okay? Now, one thing we notice is that this doesn't really help us in this form. And we have it as cos theta plus I sine theta to the 5th power. That don't help us. So we're going to have to expand this bracket. To expand this, I just want you to remember Pascal triangle. Let me put Pascal triangle up here, which are the coefficients of each term. Remember, it's 1. Then you have 1, 2, 1. Then it is 1, 3, 3, 1. All right. Then it is 1, 4, 6, 4, 1. And then it is 1, 5, 10. Then you add 4 to here, you get 10. You're going up by 1, you get 5, then 1. This is Pascal triangle, all right? It's easy to know. To look at this. You're going from 1, then you add 1, more, add 1, more, add 1 more. So you know down here would be 6. Right here now, you're going from 1, then you add 2, then you add 3, then you add 4. You do the same here, you add 1 here, and you keep 1s on the end. This is how Pascal triangle is. We look more into that when you check out the module 2 videos. Now let's get back to this. So we're going to use this one here. This is a coefficient of the 5th, the term with the 5th. So it's really cosine to the 5 of theta plus, this is going to be 5 cos to the 4 theta, 5 cosine to the 4 of theta, and that is being multiplied by I sine theta plus, it's going to be 10 times the cos cube of theta. Oh boy, we won't have enough space. 10 times cos cube theta times I sine theta square, I sine theta square plus, it's going to be another 10. Oh boy, it won't fit, so let's go around here. Plus 10 cos square theta times I sine theta cube plus 5 cos theta times I sine theta to the 4 plus I sine theta to the 5th. Yes, I know it is very lengthy. It's very lengthy to write out all of that. I know. Plus I sine theta to the 5th. And remember, all of this is equal to cos n theta, which is cos 5 theta, plus I sine 5 theta. So all of this is equal to cos 5 theta plus I sine 5 theta. So now, after you get this now, what are you going to do? Well, you see, all of this now, what do you know about complex numbers? Two complex numbers are equal whenever their real parts are equal and their imaginary parts are equal. So think of over here as x plus, this is like x plus yi, and think of all of over here as a plus bi. So we need to identify the real parts. The real parts are going to be the terms without I, and the imaginary parts are going to be the terms with I. So this is a part of the real part, cos to the fifth. Now, 5 cos to the 4, I sine theta, that's imaginary. Now, I square is minus 1, and so this will be a part of the real. All right. I cube is imaginary, that's minus I. I to the 4 is 1, so that's real. All right. So by equating the real parts, so equating the real parts, by equating the real parts, what we're going to get is this cosine 5 theta, because remember this is a real part too. We're going to get that the right hand side cosine of 5 theta is going to be equal to the real part now. Now it's cos to the 5 of theta. So cosine 5 theta is equal to cos to the 5 of theta plus, let's look what around here is. Now it says plus 10 cos cube theta I sine square theta. Now I square is minus 1, so I'm going to rewrite this as minus 10 cos cube sine square theta. All right, so this is going to become minus 10 cos cube sine square theta. Minus 10 cos cube theta sine square theta. Then this part now we know that I to the 4 is 1. So I'm going to rewrite this part as plus 5 times the cosine of theta being multiplied by, instead of saying I sine to the 4 of theta, I to the 4 is 1. So it's just being multiplied by sine to the 4 of theta. It's just been multiplied by sine to the 4 of theta. Beautiful. Now what do you do next? Now notice that in the solution, everything is in terms of cosine. So we're going to have to do some substituting. So what we're going to then get is cosine to the 5th power of theta minus, now this sine square, we know sine square is 1 minus cos square. So we can rewrite this as minus 10 cos cube theta times sine squared theta, but sine squared theta is 1 minus cos squared theta. Don't you ever forget that identity from Add Math or Unit 1. Plus, then you're going to have 5 cosine theta. Now we're going to need an identity for sine to the 4 of theta. But sine to the 4 of theta, if I can break it down, is sine squared theta all square. But sine square is 1 minus cos square. So it's going to be 1 minus cos theta all square. If you're wondering, how did I get that? 1 minus cos square theta all square. Because remember, sine to the 4 can be looked at sine square square. And sine square is 1 minus cos square. So it's 1 minus cos square all square. All right, so now we can expand this. So expanding, we're going to get cosine to the 5 of theta minus, now 10 cos cube theta times 1 is minus 10 cos cube. Minus 10 cos cube theta. Now minus and minus give us plus, and so that becomes cos cube times cos squared is cos to the 5th. So we get plus 10 cosine to the 5th power of theta plus, now we need to multiply 5 cos theta by this square. So I'm going to do it in 2 steps. This is 5 cosine theta being multiplied by, we need to work out what is 1 minus cos square theta all square. That part is going to work out to be first term square minus twice the product of the 2, which is minus 2 cos square theta plus second term square. Plus the second term square is cos square is cos to the 4. I'm going to leave off the theta here, but we know it's theta. When I just write cos to the 4, we're talking about cos to the 4 of theta. This is cos to the 4. This means cos to the 4 of theta. So now we can finally write what everything is. So what this is working out to be is cosine to the 5 of theta minus 10 cos cube theta plus 10 cosine to the 5 of theta then cos to the 5 of theta plus 5 cos theta times all of this. 5 cos theta times 1 is 5 cos theta. Then you're going to have 5 cos theta times minus 2 cos square theta. You're going to get 5 times minus 2 is minus 10. So you get minus 10 cos cube of theta. And then you're going to have 5 cos theta times cos to the 4 theta. That's going to become 5 cos to the 5 of theta. So this is 5 cos to the 5 of theta. Okay, good. Now all we have to do is just add them. Now I notice I have a cos to the 5 here. I have 10 cos to the 5 here. And I have 5 cos to the 5 here. So when I add them up, what I'm going to get is 1 plus 10 plus 5 is 16. So I get 16 cos to the 5 of theta. That's what they had. Okay, so we have a good start so far. Next thing I notice, I have cos cubes. I have minus 10 cos cube, and I have minus 10 cos cube. That's minus 20 cos cube. So that's minus 20 cos cube. Minus 20 cos cube theta. Okay, good so far. Now, what I notice is that we have just 5 cos theta. And so we'll just write back that part and we get the proof. So you just put back here plus 5 cos theta. So this is it proven, all right? Nice and easy, soft. So you can just write QED, all right? Which you can tell them quite easily done. Nice and easy, soft, quite easily done. Easy question. Now let's look at the next part. Part D. Part D is another complex part again. All right, so notice that they didn't give us much differentiation this year. They gave us more complex numbers. Part D. Part D says that write Z is equal to minus 1 plus I to the 7th in the form RE to the I times theta. So let me write that down. Z is equal to minus 1 plus I, and this is raised to the 7th power. All right. I need to write it in the form RE to the I times theta. Now, before we do this, what I like to do is to go from this form to polar form, and then from polar form to exponential form. All right, so I like to, if that is Z, I'm going to call another complex number. I'm going to call P. I'm going to call minus I plus 1 P. All right, think of minus I plus 1 as some complex number P. All right. To put this in polar form, what we know is that R is going to be equal to 1 square plus 1 square rooted. My apologies. And that's the square root of 2. So that is going to be R. The next thing you're going to need is to find the argument, but the argument depends on the quadrant that it is in. All right, so you have to remember minus 1 is here, plus I is here. So it's in the second quadrant. All right. Whenever it is in the second quadrant, it is pi plus tan inverse of y over x. All right. Once it is in the second quadrant, it's always the angle between this and the positive x-axis. All right. And so in this case, the argument of P is going to be equal to pi plus tan inverse of that looks like 1 over minus 1 is just minus 1. So you put that in a calculator, tan inverse of minus 1, which I should know, but that's minus pi by 4. And so the argument of P is pi minus pi by 4. And pi minus pi by 4 is 3 pi by 4, which makes sense. Based on our diagram, it should be 3 pi by 4. Yep, so correct. Based on our diagram, we can see that it should be 3 pi by 4. Doing a sketch always make you see what the answer should be. We know it should be between 90 and 180 based on our diagram. Yeah. All right, it's always good to give a sketch. All right, it's always good to give a sketch. So this is that. All right, now that we have P, next thing that we're going to need now is Z. All right. So now we can rewrite Z as Z is equal to, what is Z? Z is equal to R, which is the root of 2, R into cos theta, where theta is 3 pi by 4. So Z is root 2 cos 3 pi by 4 plus I sine theta plus I sine 3 pi by 4. And all of this is being raised to the 7th power. All of this, every little thing right here, so is being raised to the 7th power. All right, all of this is being raised to the 7th power. So if we're raising all of that to the 7th power, it's going to be root 2 to the 7th power, which I don't know what that is. So we're going to use the Marvelous Theorem again. So it's going to be root 2 to the 7th power times cos theta plus I sine theta to the n is cos n theta. So it becomes the cosine of 3 pi by 4 times 7. 7 times 3 is 7 times 3, 21. I know it is really sad to put that in a calculator, but it happens to the best of us. So it's 21 pi over 4 plus I sine 21 pi over 4. All right, now I can put it in the form z is equal to re to the I times theta, because right here, so I have it in, this is in the polar form, which they didn't ask for. So to put it in the exponential form, it's going to be r is root 2 to the 7th power, so it's root 2 to the 7th power e to the I times theta, e to the I times theta. I times theta is going to be 21 over 4 pi, 21 over 4 pi times I. All right, and that's that. That is z. Root 2 to the 7, e to the 21 over 4 pi times I. Nice. So that takes care of part 1. Now let's look at part 2. Part 2 says, hence, prove that minus 1 plus I raised to the 7th power is equal to minus 8 into 1 plus I. So we should hence, so it means using this, prove that this is equal to minus 8 into 1 plus I. So there are many steps I'm thinking of that we can use to prove that. But they said hence, so we need to use this principle. All right. No, that it's a good thing. That's why I did it this way, you know, guys. You see that? It's a good thing why I did it this way. All right. I'm so happy I did it this way now. So now for part 2, right? It said hence. So remember, we said that z is this, don't it? Yeah, man. We said z is this. All right. So let's write that down. We said that z is equal to root 2 to the 7th power times e to the 21 over 4 pi I. Yes, we said that. But we also know it in its polar form. We also know in the polar form, it is root 2 to the 7th power times the cosine of 21 over 4 times pi plus I sine 21 over 4 times pi. Yes. So this come in very, 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 very handy. So this part is coming in very handy now. You might look at me and you might wonder, why is that very handy? That's very handy because look at this now. Now, root 2 to the 7th power, put that in your calculator. Yes, I know it is sad. Root 2 raised to the 7th power I know how I'm going to write it now. Root 2 raised to the 7th power. Now, if you were to look at root 2 raised to the 6th power, what would be root 2 to the 6th power? Root 2 to the 6th power would be 8. So I'm going to write this as 8 root 2. All right, that's root 2 to the 7th power times, now, the cosine of 21 pi by 4. Put in the calculator, 21 pi by 4, and find the cos of that value. All right. So we're going to put in our calculator 21 pi divided by 4. The cosine of that value is, when I work out the cosine of 21 pi by 4, I get minus root 2 over 2. So I get minus root 2 over 2. That's what my calculator is giving me. Now put this in your calculator, 21 sine of 21 pi by 4. So I get plus I times now 21 over 4 times pi, and I take the sine of that value. I'm still getting minus root 2 over 2 as well. So this becomes, I get rid of this. This becomes minus root 2 over 2 times I. Now we're good to go. So now we can multiply them. Multiplying them now, what we're going to get is minus root 2 over 2 times 8 root 2 over 2. Put that in a calculator for me. 8 root 2 over 2 times root 2 divided by 2. And I get 8. All right, so I get this works out now to be this time, this is 8. And so if this is, well, minus 8, and then this gonna give me minus 8i. So all I need to do now is factor out negative 8, and I factor out negative 8, and I get 1 plus I. So the question easy, soft, with a capital T, soft. And so it is proven. So when you prove it, you can say soft, soft, the capital T. Soft. That takes care of question 1. And that's 25 marks. All right, generally question 1 deals with differentiation and complex numbers. Question 2. Question 2 typically is integration. Question 2 says, determine the integral of sine 2x cos sine x cos 2x. So it wants us to compute the integral of sine x cos 2x dx. Now to do this, I just want you to think back. All right, I'm going to rewrite this a different way. Please bear with me. I'm rewriting this a different way as you're computing the integral of cosine 2x times the sine of x. All right, just think of it this way for me, please. All right. Now there are many ways you can do this integration. You can use integration by parts, or you can do it like this. And there's a reason why I write it like this, because look where I'm going. I'm gonna make a space right here. Let me change this font color to red. All right. What am I trying to say? I'm trying to say that we learned that the sine of A minus the sine of B. We had learned in unit 1 that sine A minus sine B is twice the cos of half the sum. That's equal to 2 cos A plus B over 2 times the sine of half the difference times the sine of A minus B over 2. We learned this in unit 1. Okay, so if we learned this in unit 1, you can look at it and see that, oh, well, if I were to replace A plus B over 2 with 2x and A minus B over 2 with x, you realize that's what we have right here. Look, replace A plus B over 2 with 2x. So what you'd get is 2 cos 2x times the sine of x. And so what are you claiming? You're claiming that A plus B over 2 is 2x. All right? In order for A plus B over 2 to be 2x, if A is 3 and B is 1, 3x plus x over 2 is 2x. and 3x minus x over 2 is x. And so in that case, that means that the sine of 3x minus the sine of x is equal to 2 cos 2x sine x. Yes, yes, yes. All right, so then now, if we divide both sides by 2, dividing both sides by 2, we'll get sine 3x minus sine x over 2 is cos 2x. So what are you saying, sir? What I am saying then is this integral can be looked as the integral of, I'm going to put a half out here, a half the integral of sine 3x minus sine x. You see how this work out much easier? Sine 3x minus sine x. Nice and easy, soft. Now we can go ahead and integrate this without much worries. So integrating this, we're gonna have a half the integral of, when you integrate sine, you get, when you integrate sine, you get minus cosine. So when you integrate sine 3x, you get minus cos 3x. And then you divide that by the derivative of 3x, which is 3, minus, when you integrate sine x, you get minus cos, so minus and minus become plus. So you get plus. Oh, integrate sine, you get minus cos, so it becomes plus cos x. Plus some constant of integration, plus, call it k. Nice, so that's that. That takes care of part 1, and that's a whole of 5 marks they're giving you to do nothing. Let's look at part 2. Part 2 say, hence, calculate the definite integral from 0 to pi by 2. So I'm going to call this I, all right, because I can't bother to write out so much stuff. I'm going to call it I, all right. So if we're finding the definite integral of I from 0 to pi by 2, and I'm still going to have to write it out. Oh gosh. So if we're finding the definite integral from 0 to pi by 2, we'll find the definite integral from 0 to pi by 2 of minus cos 3x over, we're finding the definite integral of from 0 to pi by 2. All right, computer, stop freezing. The integral from 0 to pi by 2 of sine x cos 2x. We already know what the result is going to be. Result is going to be a half the cosine of that, so it's going to be a half minus the cos of 3x over 3 plus cos x, but we're integrating now from 0 to pi by 2. Just going to put the limits, which is 0 to pi by 2. Nice and easy. So let's go ahead and do this question real quick now. Now, when you substitute x as pi by 2 here, what you're going to get is pi by 2 times 3. The cos of that is 0. The cos of 3 pi by 2 is 0. Really? The cos of 3 pi by 2 is 0. So the cos of 3 pi by 2 is 0. So you're going to get a half of, when you put in pi by 2 first, you're getting 0. When you put in cos of pi by 2, cos 90 is also 0. So that part works out to be 0. All right. Minus a half of, let's put in the 0 now. When you put in the 0, you're going to get the cosine of 0, which is 1. And so this works out to be minus 1 and then the cos of 0 is 1. That works out to be equal to minus 1 plus 1 is 0. So all of this works out to be 0. So integral from 0 to pi by 2 of this is 0. Oh gosh, isn't that this sweet? All right. So the integral from sine x cos 2x is 0. Now another way we could have done this question is use integration by parts, but I didn't want to do by parts there. You could, but no need to. Soft. Let's look at part B now. Looking at part B, it says let f of x be x times the modulus of x. So it tells us that f of x is equal to x times the modulus of x. That part is not significant. I'm only going to write down that f of x is really my x squared when x is positive and minus x squared when x is negative. So this is a piecewise function. It is x squared for all positive values of x, and it is minus x squared for when x is less than 0. And it says using trapezium rule with 4 intervals to calculate the area of f of x for the domain minus 0.75 to 2.25. So first thing, we're just going to write down back the formula. We'll find area. Area is equal to a half h into half h times y naught plus yn plus 2 times everything else plus 2 times y1 plus y2, and it continue plus yn. So this is the trapezium rule formula. All right, just to refresh our memory. So first thing we need to find out is what is h. So we have to remember that h is equal to b minus a over n. H is b minus a over n, where b is the upper limit, and the upper limit is 2.25. So it is 2.25 minus 0.75, and that's divided by the number of intervals, which is 4. So you know what I'm going to say again. You put this in your calculator and see what you get for h. When you put that in your calculator, you're going to get 2.25 minus 0.75. And you get 3 over 4, which is 3/4. So I'm getting h is 0.75. Now that we get that h is 0.75, the best way to do it is the table method. You might say, sir, what table method? Well, the table method is like this. You put a table with your domain and your codomain. So let's start with the domain. The domain up here. It is 4 intervals, and we're running from the domain where x is, believe the domain are from minus 0.75. Then you add 0.75 to that, you're gonna get 0. Then you add 0.75 to that, you get 0.75. Then you add 0.75 to that, you get 1.5. Then you add 0.75 to that, you get 2.25. So that takes care of all of the domain. Nice. Now next you need is to find the corresponding y values for each of these x value. So to find the corresponding y value, you have to look to the function. you're going to have to look to the function to find the corresponding y values. All right, so y. When x is minus 0.75, then f of x is minus x squared because x is less than 0. So put in minus 0.75. So 0.75 minus 0.75 squared, and then a negative is in front of it. And so it is minus x squared, which is minus 0.5625. Then when x is 0, y is clearly 0. When x is 0.75, it's just going to be the positive of that number, which is 0.5625. Then you put in 1.5 square. 1.5 square is 2.25, I believe. Yes, 2.25. Then you put in 2.25 square, and so 2.25 square is 5.0625. 5.0625. All right, nice and easy. Okay, now let's go. Area. So the area is equal to, remember it's a half h, so it's going to be 0.5 times h. H is 0.75. All right, it's a half h times, in bracket, y naught. Y naught is minus 0.5625 plus yn. Yn is the last y value, which is 5.0625 plus 2 times the y values in the middle. Y values in the middle is 0 plus 0.5625 plus 2.25. Those are the y values in the middle. So you can go ahead now to compute the area. And so that is going to be 0.5 times 0.75. All of that is multiplied by minus 0.5625 plus 5.0625 plus 2 times 0 plus 0.5625 plus 2.25. You close up those brackets, and I'm getting the area is 3. Did they set to round it off? They didn't set to round it off, so that's 3.79685. So just want to check that I didn't make any additional errors. Sometimes you can make additional errors, so you just want to check it again. Don't be afraid to check over your work. All right, so we're fine. So that's the area, and remember, area is units square. All right, so that's part B, soft, a capital T. Part C. Part C say, show that 2x squared plus 4 over x squared plus 4 all squared is equal to 2 over x squared plus 4 minus 4 over x squared plus 4 all squared. So to do this, we're going to have to use partial fraction. All right, so we're going to have to use partial fraction to do this. All right, so we need to show that 2x squared plus 4, and all of this is divided by x squared plus 4 all square this is equal to, well, in order to separate this in partial fraction, all right, it's going to be ax plus b. So it's ax plus b over x squared plus 4. Now you have to remember the different formats, all right? This is known as a quadratic that is irreducible, that is repeated. And so the irreducible quadratic that is repeated, it takes the form of ax plus b over x squared plus 4 plus cx plus d over x squared plus 4 all squared. All right, and then now we're gonna have to solve for a, b, and c. In order to solve for a, b, and c, what we're gonna have to do is we're gonna first find the LCM. So we're gonna find the LCM between these two. X squared plus 4 and x squared plus 4 all square. That's gonna have a LCM of x squared plus 4 all square. And then you're going to say x squared plus 4 into this leaves x squared plus 4. And so what this works out to be is ax plus b. This is ax plus b multiplied by x squared plus 4 plus x squared plus 4 all square into this, just leaves back here with cx plus d because it goes into that one time. Now, whenever the denominators are the same, all you do is equate your numerators. Nice, because remember over here was just x squared plus 4 all square in the denominator, and in the numerator we just had 2x squared plus 4. So whenever the denominators are the same, we equate the numerators for the two fractions to be equal. So let's equate the numerators. We can't fit it here. Well, we can. Let's try and make it fit here. All right, so equating the numerators, what we're gonna get is 2x squared plus 4. Equating numerators, 2x squared plus 4. We're gonna get that is equal to, now, right here we have ax plus b times x squared plus 4. We can expand that to get that this is going to be equal to ax cubed. It's ax cubed plus 4ax, ax cubed plus 4ax plus bx squared plus 4b. Nice and easy, soft. So this is what we have now. 2x squared plus 4 is equal to ax cubed plus 4ax plus bx squared plus 4b plus cx plus d. All right, that's what we have. Now notice that there are no x cubed terms over here. And so what we can conclude then is that since there's no x cubed term, ax cubed must equal to 0, because you must have a 0x cubed here. So what we're concluding then is a must be equal to 0. Then we need to equate our x squared terms. The x squared terms we have 2x squared here, and we have a bx squared here. And so 2x squared must equal to bx squared. And so our conclusion must be that b equal 2. It has to be b equal 2. Then we don't have no x term here, so And how many x terms we have here? We have 4ax plus cx. But remember, a is 0. And so 0 plus 0 must be a 0. And so c must also be 0. Oh, so c must also be 0. So clearly, c must equal 0. Then finally, to equate our constants, let's find our constants. Finally, our constants, we have 4 is equal to 4b plus d. So 4 is going to be equal to 4b plus d. 4 is equal to 4b, but what is 4b? 4 times b is 8. So that's 8. That's 4b plus d. So if 8 plus d equal 4, then d must equal to negative 4. All right. So nice. Now that we get a, b, and c, now we can say hence 2x squared plus 4 over x squared plus 4 all squared. Hence 2x squared plus 4 over x squared plus 4 all squared. This is clearly equal to ax plus b. Ax plus b, where a is 0, b is 2. So it works out to be 2 over x squared plus 4 plus cx plus d. Cx plus d, c is 0, d is minus 4. So it just works out to be plus minus 4. But instead of saying plus minus 4, why not just write minus 4? So let's write minus 4 over x squared plus 4 all squared. Right. Nice and easy, soft. And so we've shown that. So you're right, shown. Soft. Let's look at the next part of the question. The next part of the question goes further to say, hence, find the integral of 2x squared plus 4 over x squared plus 4x using the substitution, x being 2 tan theta. So it gave us a substitution that we have to use. All right, you have to. So let's go ahead and do that using the substitution they give. Okay. So part 2. So we're going to write now that the integral of 2x squared, when it says hence, guys, when it says hence, it means you're going to have to use up what you did previously. So we're going to say the integral of 2x squared plus 4, 2x squared plus 4 over x squared plus 4 all squared. This integral right here is going to be equal to the integral of 2 over x squared plus 4. It's going to be equal to the integral of 2 over x squared plus 4 dx minus the integral of 4 over x squared plus 4 all squared. All right, nice and easy. That's what we're doing. Soft, a capital T. Soft. Okay, now that we're doing this, what do we need to do? Well, first thing that we're going to need to do is, it says using the substitution, x is 2 tan theta. So if x is 2 tan theta, then what is going to be dx? If x is 2 tan theta, then dx is equal to, when you differentiate tan theta, you'll get sec theta. All right, and so dx is equal to 2, differentiate tan to get sec square theta. All right, so dx is 2 sec squared theta d theta. So we're going to substitute those now. So substituting those right here, this is going to work out to be equal to, now replacing x with tan, so it's going to work out to be the integral of 2 times, now this dx, guys, is 2 sec squared theta. So it's 2 times 2 sec squared theta. So it's 2 times 2 sec squared theta d theta over, now x squared, x is 2 tan theta, so x squared is going to be 4 tan squared theta, 4 tan squared theta plus 4. Then we're going to have minus the integral of, again, dx is going to be 2 sec squared theta, so 2 sec squared theta times 4. The numerator, we're going to get 8 sec squared theta d theta. And then let's work out the denominator. In the denominator, we have a square. It's going to be first term square, which is x to the 4. But x squared plus 4. All right, x squared plus 4. X is 2 tan theta. 2 tan theta square. Let me just write it this way. 2 tan theta square. 2 tan theta square is 4 tan squared theta plus 4 all square. Now guys, 4 tan squared theta plus 4, this is 4 sec squared theta. Remember sec squared theta. All right, so let me write down that identity again up here. Let's use a different color ink. Just to refresh our memory, we need to remember that sec squared theta is equal to 1 plus tan squared theta. That's sec squared theta, 1 plus tan squared theta. All right, sec squared theta is 1 plus tan squared theta. So if you multiply sec squared by 4, then what you get is 4 sec squared theta is going to be 4 plus 4 tan squared theta. So 4 sec squared theta is 4 plus 4 tan squared theta. So what does that mean? That means that in the numerator where we have 4 sec squared theta, in this denominator is also 4 sec squared theta. So this is really just the integral of 4 sec squared theta over 4 sec squared theta. That's what we really have in the denominator right here. So we have 4 sec squared theta over 4 sec squared theta. Nice and easy. Soft. All right. Minus, now 4 tan squared theta plus 4, remember that's 4 sec squared theta. So really have minus the integral of 8 sec squared theta over 4 sec squared theta squared over 4 sec squared theta squared. 4 sec squared theta squared. That's what we have. So now guys, we can go ahead and compute. Would have liked to have a little more space. Now this is going to be equal to now 4 sec squared theta over 4 sec squared theta is 1. And when you integrate 1, so let me just show that this cancel right here. So canceling in red, 4 sec squared theta cancels 4 sec squared theta. So you're integrating 1 d theta, and the integral of 1 is just theta. Nice. Now, in this denominator right here, where you have 4 sec squared theta, When you square it, it's going to become 16 sec to the 4th theta. So if I were to just square it, so I'm going to take rid of the square here, and I'm just going to square it. If I were to just square it, instead of writing 4 there, square it to get 16 sec squared theta. All right, so 8 sec to the 4, sorry, sec to the 4 theta. 8 over 16, sec square cancel out sec square. So I'm going to get minus the integral of, so theta minus the integral of 8 cancel out 16. So I'm getting sec square over sec to the 4 is just sec to the minus 2. So I'm going to get 1 over sec square theta. 1 over sec square theta times 2. Wonder where the 2 come from? 8 over 16. 1 over 2. So I get theta minus 1 over 2 sec square theta. Now guys, that's now easy. Now look at this, theta. Remember we said that x is 2 tan theta. So if x is 2 tan theta, we can divide both sides by 2. X is 2 tan theta. Let me write it back over here. We're saying if x is 2 tan theta, if x is 2 tan theta, if you're to divide both sides by 2, you're going to get x over 2 is tan theta. You're going to get x over 2 is tan theta. And if x over 2 is tan theta, right, you can take the inverse, the tan inverse, and you're going to get theta is tan inverse x over 2. All right, theta is tan inverse x over 2. So, sir, what are you saying? I'm saying that instead of putting back theta now, give them the answer in terms of x. So instead of saying theta, it's going to be equal to tan inverse x over 2, because remove the theta now. It's tan inverse x over 2. Right here, this is tan inverse x over 2 minus the integral of 1 over sec square theta. Now guys, 1 over sec square, 1 over sec square is cos square. So this is cos square theta over 2. Cos square theta over 2 can be written as minus a half the integral of cos square theta. I know it's a lot of work to do this question, but now we get it when it reached this now easy, integrating cos square theta. Guys, to integrate cos square theta now, we're gonna have to jump back to another identity. You have to remember that 2 cos square theta minus 1, that's equal to 2 cos square theta minus 1 is equal to cos 2 theta. All right, and so if we were to make cos square the subject from here, we're going to see that cos square theta is equal to 1 plus cos 2 theta over 2. All right, cos square theta is 1 plus cos 2 theta over 2. 1 plus cos 2 theta over 2. All right, and so all we have to do now is replace this now and say this is equal to tan inverse. This is now equal to tan inverse of x over 2 minus a half cos square theta, but a half the integral of cos square theta is the integral of 1 plus cos 2 theta, 1 plus cos 2 theta over 2. That's what we're integrating. So finally now we can finish. Yes, I know I said finally so many times, but finally now we're really done. So this is now just tan inverse of x over 2. This is now tan inverse of x over 2 minus, factor out the 2 out here to become minus a quarter of, when you integrate 1, you get theta. Then when you integrate cos 2 theta, when you integrate cos, you get sine. So you get plus sine 2 theta over 2. Plus some constant c. Now guys, we know what theta is. Theta is tan inverse x over 2. So you're going to have to write out all of that. So finally, the final answer is tan inverse x over 2 minus a quarter of this theta becomes tan inverse x over 2 again. Minus a quarter tan inverse x over 2 plus sine 2 theta. Sine 2 theta is now the sine of 2 times 2 theta. If you just put a 2 here, it would be the sine of 2 times tan inverse x over 2. It's a sine of 2 times tan inverse x over 2 divided by 2 plus c. Guys, you could simplify this in so many ways, because given that you know what tan theta is, given that tan theta is x over 2, you could simply, you don't have to even write it like this. What am I saying? If you know that tan theta is x over 2, you can draw your triangle. All right, tan theta is generally opposite x over adjacent 2. So if the opposite is 2 and the opposite is x and adjacent is 2, you could find hypotenuse by saying that the hypotenuse is going to be x squared plus 4 all square rooted. That would be the hypotenuse. When you get the hypotenuse, right, you could have even went further to say that sine 2 theta is 2 sine theta cos theta. So you don't even need to write it like this. You could go further and say that the answer is so many ways you can write the answer. Remember, sine 2 theta is 2 sine theta cos theta. And 2 sine theta cos theta over 2 is just sine theta cos theta. I'm saying this part right here is the same as sine theta cos theta. This part right here is the sine theta cos theta. And sine theta would be opposite over hypotenuse. So you could say that that is equal to the sine of sine theta, which would be opposite x over hypotenuse, sine x times the square root of x squared plus 4 times the cosine of theta, and the cosine of theta would be 2 over x squared. Cosine of theta would be adjacent 2 over the square root of x squared plus 4. There are many ways you can write your answer. Many, 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 many ways. So this question was nice and easy, soft, but very long. It was very long. I must agree that it was very long. Plus your constant c. Soft. So finish module 1. That takes care of module 1. So let us continue and we'll go on to module 2. Module 2 says the sequence AN is defined by